So last time we have seen several examples of how we can use the basic probability to solve some problems in combinatorics. Today we will see more examples. More examples of how we can again use the probability to solve some combinatorial problems. So let's consider some examples on hypergraph. So before we consider some examples on the graph, and last time we also defined hypergraph. So we define hypergraph as a tuple which consists of the vertices and edges. And edges are the collection of subsets of vertices. And we say this is K uniform hypergraph, or simply K graphs, if every edge has size K. And for this hypergraph, we also can consider some concepts which we considered in the graphs. For example, we can consider matchings or connectivity or coloring. So we say that given hypergraph H has property B, or simply it is two-colorable. So these, both of them are, same thing. So this is definition. There are several, names for it because at the early time people have called it the property B, but which is essentially what it means to be two-colorable. So for graph case, when do we say a graph is two-colorable or bipartite? If you can color the vertices so that no two adjacent vertices get the same color, which is same as if you consider this edge as a set of two vertices, and this forbids a monochromatic edge. So we also want to find the coloring with two colors. So here two coloring of V is a function from V to say two colors, which is 1 and 2, such that no edge is monochromatic. And let MK be the minimum possible number of edges of an K graph that is not two-colorable. For example, if K is 2, then for graph case, what's the minimum number of edges in a graph which is not two-colorable? If you consider a triangle, K3, it has 3 edges, not colorable, not two-colorable. On the other hand, if you have only 2 edges, then the graph is either this or this. So it's two-colorable. So in this case, M2 is 3. So what's the value of MK? So that's a question. Can we find some estimate? So one of the easy way of finding an example. So here we find the upper bound. So by presenting one example, we get an upper bound. And by generalizing this example, what we can consider is that we consider a complete K uniform hypergraph on 2K minus 1 vertices. So which consists of the edges, whose edge is that we consider all possible, let's say, write it this way. H set of this is that there are 2k minus 1 vertices, and we consider all k, set of k vertices as edges. Then you have 2k minus 1 vertices, and you have 2 coloring, red and blue. Then by pigeonhole principle, one of the color, say blue, contains more than k vertices. Then you collect those k vertices, then they form an edge, which is a monochromatic edge. So if you have this hypergraph, this k graph, then no matter how you color the vertices with 2 color, there always exists a monochromatic edge. So this is not 2 colorable. Then how many edges does it have? It has 2k minus 1 choose k edges, which provides an upper bound on this mk, which is roughly 4 to the k over square root of pi k. If you use the Stirling's formula, so this is exponential. So we have this upper bound, and what lower bound can we prove? So how do we want to prove a lower bound again? So just like the Erudice's theorem on the lower bound of the Ramsey's number, what you can do is you consider a random coloring. Then we can prove this. So whenever we have a k uniform hypergraph with less than 2 to the k minus 1 edges, this is 2 colorable. In other words, m of k is 2 to the k minus 1 at least. We get this lower bound. And how do we prove it? Again, if we randomly color the vertices with 2 color, then for a given edge with k vertices, what's the probability that this becomes monochromatic? We know that this is 2 to the 1 minus k, which is exactly the reciprocal of this. Then, we can easily guess what's the strategy. If we have a k graph with less than 2 to the k minus 1 edges, let's write it this way. E of h to denote the number of edges in the hypergraph. Then what we do is we color the vertices in V by 2 colors independently, uniformly, and random. So for each vertex, we flip a coin and then we color it with one of the 2 colors, red or blue. For each edge E, we let AE be the event that E is monochromatic under this random coloring. Then what's the probability of this event? It's 2 to the 1 minus k. Then if you consider the probability of at least one event happens, at least one edge become monochromatic, it's bounded by the probability of each one of them, and then the number of edges times which is at most 2 to the 1 minus k, which is strictly more than 1. So that means with positive probability, this minus this is positive. So with positive probability, we can actually avoid all these bad events. So this shows that there is 2 coloring. without monochromatic edges. So we have a lower bound, which is roughly 2 to the k, and we have an upper bound, which is roughly 4 to the k. So for the Ramsey number case, there was again the large gap between upper and lower bound, and the gap is actually, still remain. But for this MK, the two colorability case, we can actually also prove the upper bound using probability. So how do we use the upper bound to show, how do we use the probabilistic method to show upper bound? For lower bound, we just have to present coloring. So for given H, we present a coloring. Then that's the lower bound. For upper bound, we have to find H, which is not too colorable. So for lower bound, we have to find the coloring. So we find the random coloring. But for upper bound, we can find the hypergraph. So we can randomize this. So we can choose a random hypergraph and then compute the probability that this is not too colorable and show that that's positive. That's a possible strategy to find an upper bound. So we can prove this. There is this K uniform hypergraph with 1 plus log of 1 times E times log 2 for k squared 2 to the k edges that is not too colorable. By the way, last time we defined this big O theta, big omega. I think we didn't define theta. Little o, little omega. We defined these four. So I said that Fn is big O of Gn if and only if Fn is smaller than C times Gn for some. So there exists C such that this happens for all n. But I was slightly wrong that we have to actually put this absolute value. So for our convenience, we want to say that negative n is also, big O of n squared. Because in that case, we don't have to put plus minus here. So, we just want to make sure that this term goes to 0. So this is for big O, but similarly for small o. Small o is that for all epsilon positive, there is n0 such that this is smaller than epsilon times that for all n at least n0. So we want to write it this way as long as, this function goes to 0 when we divide this by Gn. So this and this are essentially same. So we want to, forget the sign and then we compare these two. So that's, what we want to do. And last time we didn't define theta and we say the f of n is theta of g. If, this is big O of g as well as big omega of g. Then we say that f of n is theta of gn. So in other words, we can bound gn by the constant multiple of f, either from upper bound or lower bound. the other way around. We can bound f by the constant multiple of g from above and from below. Anyway, so from that, so this is just some function goes to 0, which as k goes to infinity. So this is some term which goes to 0 as k goes to infinity. But it could be positive or negative. Anyway, back to what we were doing. We want to show that there exists a k-uniform hypergraph, which is not two-colorable and has this many edges. So how do you want to do it? We want to consider a k-graph with m edges and vertex set bracket n. And m and n we will not specify yet. Will be chosen later. Then, now what we want to do is we want to construct H at random and then show that this is not two-colorable with positive probability. And how do we show that it is not two-colorable? We say that it is not two-colorable if any two coloring we take, they are not proper. That means they always give some monochromatic edge. No matter how we color, it provides a monochromatic edge. Then it is not two-colorable. So what we will do is we consider all possible coloring. And then estimate the probability that for this graph, these colorings are all bad. So we fix a coloring with R vertices in a color and S in the other color, where R plus S is N. What's the probability that randomly chosen K set of size K is monochromatic? Is R choose K plus S choose K over N choose K. So this is the number of all sets of size K, and then these are the number of monochromatic edges with this specific coloring. And we know that this is at least, so this is minimized if R and S are same or off by 1, because x choose K is a convex function, which is x times x minus 1 times x minus k plus 1 divided by k factorial, which is actually a continuous function. Here x can be real number. Then this is a convex function, so we can actually show that this is minimized when R and S are same. So, even if n is odd number, we can actually write that as it's minimized when, when we have n over 2 choose k. Let's say this is p. And we know that this probability is always as at least p. Then, for a fixed coloring, say sigma from the vertices to 0, 1 is we know that H, I mean the random K subset of N is monochromatic is at least P. So now what we do is we choose M edges of size K independently, uniformly, and random with repetition allowed. So it's okay if we choose same edge twice. Then what's the probability that none of them are monochromatic? So for this fixed coloring, we choose, M edges of size K uniformly random. Then probability that none of them are monochromatic is at most 1 minus P to the M. So we have chosen M edges. So each edge must avoid this bad event, which happens with probability P. So it can avoid that with the probability 1 minus P, at least 1 minus P. And then you do it M times independently. So it can avoid, each edge can avoid the, this bad event with probability n most 1 minus P, because this is a lower bound for bad event. So this is upper bound for good event. So at most this much. So how many, now we want to apply the union bound. How many coloring are there? There are 2 to the n possible coloring, at most 2 to the n possible coloring. And each has probability at most 1 minus P to the M of being a proper to coloring. Here, proper to coloring means that it can avoid all monochromatic edges. So, by union bound, we have a upper bound of the probability that our set, H is two colorable, is bounded by this number. So H is obtained by choosing M edges uniformly at random, independently uniformly at random. So you choose one set of size K, and then second set of size K, and third set of size K, and so on. Then you get all the edges, and that's our H. And this is two colorable, means that at least one of the possible coloring is actually a good coloring, which has the probability by union bound at most this times 2 to the n. So this is the upper bound. So if 2 to the n times 1 minus P to the m is smaller than 1, then there exists a K graph with n vertices and m edges, which is not too colorable. So now what we only have to do is we can choose m and n in a nice way so that this holds and m is as big as possible. So we seek to, m is as small as possible. We seek to minimize m such that this holds. So again, this expression is not so good, so we know that this holds. So as long as we can ensure that this inequality holds, then this follows. So it's enough to find the m so that we can minimize this. So here you take a logarithm, then n log 2 minus mp smaller than 0. So this is what we want to achieve. So how do we want to achieve? Of course, you just take the m to be the ceiling of n log 2 over p. Then this satisfies. Log 2 is an irrational number. Okay, being strict or not is not really important because this is also strict, so let's just say this. So now we want to choose in this way, but what's n? So we want to now choose n so that this is minimized, which is n over p is minimized. So what's p? P is 2 times n over 2 choose k over n choose k, which is 2 to the 1 minus k, and then you multiply n minus 2i over n minus I, which is 2 to the 1 minus k multiply by, so what's each one of them? It's essentially 1 minus I over n minus some term which is almost quadratic. And this is roughly, e to the I over n, e to the minus I over n, and the remaining terms are, small. Here we are, we can ignore this because I is at most k, and then n is some number that we will later choose as much bigger than k. Then, what do we get? The p is approximately 2 to the minus k, 2 to the 1 minus k, e to the minus k squared over 2n. So if you multiply these all together, and plus some smaller term. So, which can be kind of ignored as long as we make sure that n over k goes to 0. So, what do we have to minimize? np is n times 2 to the not np, n over p, k minus 1 times e to the k squared over 2n. So this is some function that we can use some calculus, and we'll take the derivative and then find the extremal point, and then you can actually conclude that the setting n equal k squared over 2 is roughly asymptotically optimal. Then what do we get? Then m is, actually we can compute this in this way. So with this choice, this and this choice, we can actually show that this is smaller than 1. That means with this procedure, the randomly constructed graph H has a positive probability of being not too colorable. So there exists not too colorable hypergraph H with this many vertices and at most this many edges. Here at most, because how did we construct H? We construct H in a way that you choose one edge of size k and then add it, and then you choose another edge, add it, and another edge and add it. There is possibility that two of them actually yields the same edge. Then, the resulting H could have a, smaller number of edges than M. But, that's still okay because we, want to find the upper bounds with M most, say. So this provides an upper bound of Mk, which is M most 1 plus root of 1 times this constant times k squared and times 2 to the k. So we have again upper bound which is essentially 2 to the k with some polynomial here, k squared, and the lower bound is 2 to the k. So there is still gap of roughly, this multiplicative factor of the polynomial. So later we will close this gap a bit more in a later chapter, but still there are some gaps between, but we will come back to it in a later chapter.